let me start with a fun fact. And that is that, did you know, Anthony, that in 1966, Seymour Papert created the Summer Vision Project.
Oh, I did not know that.
And his idea was to create a significant part of a visual system which can do pattern recognition.
Okay.
In 1966. And they did break this down into sub-problems which can be solved independently. Mm-hmm. Right, because doing pattern recognition in one summer in 1966 is a hard task. So examples of subgoal is dividing the image into regions, such as likely object, likely background area, and chaos. And I don't know what class chaos is, but I want more of this.
But do you?
Yeah, as I said, I was just reading the technical review today. But what they wanted to do is use shape and surface properties. And extensions they thought of for the end of summer, like in August, would be handling objects with complex patterns and backgrounds, such as a cigarette pack with writing and bands of different color, tools, cups, etc. Which shows that in that time it was still normal to smoke and have your cigarette packages in the workplace.
I think they probably came with your desk when you got hired.
Yeah, it's such an interesting look at how life was in 1966. The other fun fact I have, by the way, is that in 1980, this person, Simon Papert, he wrote a book, Mindstorms, Children, Computers, and Powerful Ideas, where his thesis was that children can learn faster and be more social when they are using computers for learning. And this book is what Lego named their robotics kits after.
Very cool. Those things were really fun to play with, too.
The Lego Mindstorms robots are amazing. Yep. You get any project done quickly instead of having to play around with installing operating systems and Linux and whatever. It's amazing.
Very cool. I did not know that.
Welcome to Generally AI Season 2, Episode 3, where I, Roland Meertens, will be discussing the AI winter with Anthony Alford.
That's right, Roland. I'm really looking forward to it.
Yeah, so I found an AI algorithm which was invented before the first AI winter, which is still relevant today. And you actually looked up all about the AI winter. So shall we start with what you did?
I shall. Hopefully I'm not going to steal any of your thunder because a lot of the technologies that have come and gone through the AI winters are still here with us. And I'm going to weave that into the story. And by the way, when we're recording this in July and I'm in the Northern Hemisphere, it's really not winter. It's summer. It's pretty hot. So I kind of would like a little winter at this point.
Even in London, the weather is warm today, which is very rare.
It's a high of like 25, 27 degrees centigrade. You know, we laugh at that. But anyway, I digress. Those of our fans who are still following us after the first season may remember we talked about Alan Turing and Claude Shannon and how they both made early contributions to AI. And you probably remember that they did this a very long time ago. The term artificial intelligence was coined in the 1950s.
Where they also wanted to invent AI over the summer. I see a pattern.
The summer of AI followed by the AI winter, not to foreshadow, right?
Yeah, indeed.
So when people talk about AI these days, of course, they mean neural networks, they mean deep learning, they mean ChatGPT. But the key technology is the neural network. That was not always the case. Actually, throughout the years, AI researchers have explored a lot of technologies like symbolic logic, like trees and search. But neural networks have been around for just about as long as AI has been around. And hopefully, not to steal your thunder, but that it was there before the first AI winter and is still around.
I will talk more about your search algorithms.
Okay. Well, in 1957, a scientist named Frank Rosenblatt developed the perceptron. And I probably don't have to explain neural networks and perceptrons to our audience, but why not? We've got time. A perceptron is a mathematical model of what a single biological neuron does. It has several numeric inputs. It computes a weighted sum of those inputs. So each input has a different weight. and then it thresholds that weighted sum to decide whether to fire its output. The magic, though, is that you don't have to figure out yourself by hand or by thinking what the weight should be. You teach the perceptron what the weight should be using supervised learning.
Did he already look at backpropagation, or like it's only a single neuron, right?
That's right. He did not use backpropagation, but his learning algorithm had, you put the inputs in, you knew the expected output, you got the actual output, and you could difference that. And then there's a simple update algorithm to update the weights.
Oh.
And then you do this with a bunch of input-output examples, do it iteratively, adjust the weights until it gets as correct as you can. And Rosenblatt actually wrote a software implementation of this, perceptron. I think he had a bank of perceptrons. It could classify a 72 by 72 pixel image. They actually used patterns on a punch card for the images, the image inputs. He did a set of experiments, and in one experiment, he showed the perceptron could distinguish between the letter E and the letter X, even if they were rotated, and do it about 95% of the time, which is not bad for 1960.
Yeah, even when it's rotated, quite big grids on punch cards.
I don't know how big an angle of rotation, but probably a few degrees, I think.
Yeah.
But, you would think in 1960, if they could do this kind of computer vision, why didn't we get Chat GPT in the 70s and AGI before Y2K?
Compute and not enough GPUs.
Well, yeah, that was one reason. But also, your guy Seymour Papert and Marvin Minsky, they published a paper in 1969. They had done research showing a severe limitation of perceptrons.
Oh, I think I know what it is.
You know what it is. It can only learn a line. Technically speaking, it can only discriminate between classes that are linearly separable by a hyperplane. So the classic example is a perceptron cannot learn the XOR function, the exclusive OR function.
Yes.
So a lot of people gave up on perceptrons. Now, of course, perceptrons weren't the only thing in AI. There was a lot of other rumblings in the AI field. Apparently, I didn't know this, there was that computer vision project in the 60s, but there was also a machine translation project in the 60s that was not meeting expectations. So this has that classic story, which is too good to be true, but it's illustrative. You could put in the English text, the spirit is willing, but the flesh is weak. Translate that to Russian, and then translate the Russian back to English and get, the vodka is good, but the meat is rotten.
Yes. I heard of that example before. It's so funny.
Yeah. Probably it's not true. The good stories are never true, but
yeah,
it's good.
But still, it could be true.
It could be true. So in 1966, the US government pulled its funding from machine translation. In 1973, the British government published a report called the Lighthill Report that criticized the lack of progress in AI, and they subsequently cut funding for AI research in their universities. In the US, DARPA was funding a lot of AI. In 1969, they changed their policies to no longer fund undirected research, but instead to focus on concrete projects with obvious military applications. And after the Lighthill Report, DARPA didn't fund a lot of AI research either. So the end of AI summer had come. It was AI winter.
The end of the free money.
Yeah. Now, that doesn't mean there was no AI research going on at all. In fact, some people dispute the fact that there actually was an AI winter based on things like people enrolled in AI organizations like special interest groups and so forth. But the funding was definitely dried up.
Yeah, so there were still people studying it, or like students starting or being interested in AI.
Right. There were, of course, labs like the Stanford AI Lab and Carnegie Mellon, but the scale and the funding globally had been reduced.
Yeah.
And in fact, some people were actually still working with perceptrons, but now they were calling this a more general term of artificial neural networks. In their paper, Minsky and Papert did say that neural networks could learn exclusive OR and other nonlinear functions if you had multiple layers of perceptrons. So Rosenblatt just had a single layer, but if you had multiple layers where the output of perceptrons are the input of the next layer of perceptrons, you could learn nonlinear functions. In fact, you only need a single hidden layer to learn exclusive OR.
Yeah.
But nobody knew how to do the training algorithm for them.
Okay. So, I mean, you can easily show that with the right weights, you can solve XOR, right?
Yeah.
But nobody knew how to do this backpropagation.
Right. And that's in fact what happened. So around 1985, a group of researchers, including Jeff Hinton, which is a name you may know, they came up with an algorithm for training these multi-layer perceptron networks, gradient descent with backpropagation, aka backprop. What's funny is Hinton's paper literally says that the mathematical derivation of it can be omitted by the reader who finds such derivations tedious, which I think that's definitely me. So I'm going to skip over that. I think probably, again, most of our listeners are familiar with gradient descent and backprop. And in fact, those ideas were not new in 1985. It's just that nobody had applied them to neural networks until then.
Yeah. Neural
networks were back. It was the summer of AI again.
Yeah. What are we going to do now?
Well, in 1989, a researcher named Jan LeCun, again, another name you may know, he was using multi-layer neural networks to recognize handwritten digits, 16 by 16 pixel images, and he was getting 95% accuracy. So AI was back.
Pretty good. I assume that here the applications are things like sorting letters in the post office.
Again, you're familiar with this. Yes, he was doing digit recognition for, I think, post office applications.
Yeah, interesting.
I remember the early 80s, and it was a great time in so many ways. Men Without Hats and the Safety Dance and other things. And there was an AI boom. There were things like expert systems, which were very popular. And in Japan, the Japanese government had started to spend a lot of money on their 5th generation computing project. And in the US, DARPA was doing something similar. But guess what happened?
I'm feeling that there will be a second AI winter.
A second AI winter, 1990s. Rock and roll was over and it was grunge and flannel shirts because of the AI winter being so cold. Yes, AI winter. And for neural networks in particular, people were running up to limits there. The backprop training algorithm worked, but it didn't work great on very deep networks with lots of layers. I'm sure you know what the problem was.
I'm assuming there will be vanishing gradients or exploding gradients.
That's exactly right. And you'd mentioned hardware earlier. It was slow. It was the 80s.
Also, amount of data. How many data sets can you fit on a floppy disk?
Exactly.
This is even before the small floppy disks.
Yeah, we had the 8-inch floppy disks. But yes, you're exactly right. So the gradients were a problem. The hardware was a problem. And the data sets were a problem. So again, AI winter in general and for neural networks in particular. So let's skip over the 90s and the early 2000s and let's get to the part of the story that was actually feels like it wasn't that long ago. But if you think about it, it was 2012.
Yeah.
2012.
Yeah.
It's 12 years, Roland.
Yeah. Time flies.
Time flies. So Hinton and some of his colleagues at Toronto had published their results. They were using the MNIST data set of handwritten digits, which is similar to what LeCun was using in 89. They were getting better than 99% accuracy. But the gold standard, of course, of recognizing objects and images by then was ImageNet. ImageNet had come, and there's the data set problem solved, right?
Yeah.
Millions of images, 256 by 256 pixels.
Yeah, or of loads of different types of objects. Fei-Fei Li made this data set.
Exactly, and certainly kicked off the modern era of deep learning, I think. And then using that, one of Hinton's students trained a neural network that got about 85% accuracy compared to the previous record of less than 75%. So that was AlexNet, right?
Yeah.
And so those two nets, ImageNet and AlexNet, had really kicked off the age of deep learning.
Yeah.
And it's been endless summer ever since.
Yeah, it's crazy that we keep seeing that the more data you give these networks and the bigger you make these networks, the more they can learn.
And in fact, I think it was OpenAI, that's pretty famously their laws of scaling that they've plotted that. It's a power law. You can, as you increase data, as you increase model size, as you can increase training compute, the training loss is predictable.
But would you then say that the second AI winter lasted till 2012?
Well,
When would you say that the second AI winter started and ended?
These things are always kind of like it's not a bright line like the solstice or whatever, but it's certainly the 1990s and the early 2000s are considered to be like one AI winter. And so you might start thinking, well, when is the next AI winter?
Yeah, when are you predicting that we will all be fired and need to find a new job?
What if I told you that it already happened?
Oh, tell me more.
So, of course, as I said, since 2012, it's been nonstop AI, and we're so used to hearing about it now all the time. But apparently, in late 2018, early 2019, people were predicting another AI winter. There were headlines and think pieces talking about deep learning has reached or would soon reach its limits.
Yeah.
And this talk continued through 2019 and on into 2020. And in fact, if you look at things like the number of AI publications, according to Wikipedia, for the years 2021 and 2022, it actually did drop. The number of publications dropped like 30%.
Interesting.
But then, of course, was that AI winter or was it a global pandemic?
Yeah. Although I do feel that in 2018, people were very excited about seeing the performances of networks go up a lot every year.
Yes.
And we basically said at that time, perception is solved. Like it's a solved problem.
More or less. So what's interesting is, well, of course, that 21 and 22 was really a blip, right? December of 2022 was the release of ChatGPT. And since then, we've had almost 2 years of constant AI summer. We have a heat wave of AI. But people are still predicting another AI winter any day now.
Yeah. It can't always go up, right?
Exactly.
Unless one day we all work in AI. Everybody is working at an AI company nowadays.
And in fact, people like LeCun are saying things like, these LLMs, while impressive, they will not give us AGI. They're not general intelligence.
Yeah.
LeCun has been pretty vocal about that. Some people disagree. Some people think LLMs can do it. But back to AI winter, you've probably heard of Rodney Brooks.
Yes.
He's the guy that founded iRobot. He's been working in AI for my entire lifetime.
Yeah.
He has a blog where in 2018, he made a bunch of predictions about future technological advances, things like autonomous vehicles and space flight and AI. And he updates these every year with like, how has he done?
Yeah.
What's interesting in 2018, so around the time people were predicting the limits of deep learning, predicting a new AI winter, he wrote on his blog, he predicted that the next big thing in AI would happen no earlier than 2023 and no later than 2027. And he said, I don't know what this is, but whatever it turns out to be, this is a quote, whatever it turns out to be, it will be something that someone is already working on and there are already published papers about it. He said that in 2017.
Yeah. So what would you refer to as the next big thing?
In January of this year, he said it's ChatGPT.
Yeah.
So, and as we know, we talked about last season, the T in GPT, the transformer, the paper was published in 2017.
Yeah, indeed. Yeah.
So he's taken a victory lap on that prediction.
Yeah, but it's also an easy prediction, right? To say there will be a next big thing in the next 5 years and someone is already working on it.
He said that exactly. He said, I've seen this so many times. I know that, the next big thing is always going to be somebody's working on it and 5 years later.
Yeah.
What's interesting, in that same blog post in January of this year, he predicted another AI winter. He said AI winter is just around the corner and it's going to be cold.
Yeah. How cold is it going to be?
I don't know. Personally, I don't have a prediction. I just know that people like that, I obviously respect Brooks a lot and respect his prediction. On the other hand, this is sort of like that thing about so-and-so has predicted 9 of the last 5 recessions. It's very easy to predict there's an AI winter. If you just say, it's going to happen next year, it's going to happen in a couple of years, you'll eventually be right.
Yeah, true. And also there will always be one person correct. And that's the person you talk about. Survivor bias.
Right. But again, he's been through this so many times.
Yeah.
He's probably got good reasons for thinking it.
How was it for you, Anthony, to live through the AI winter?
What's interesting is I was doing my own grad school research in, it wasn't AI, it was intelligent systems,
Yeah.
intelligent robotics in the late 1990s,
Yeah.
which was certainly during one of those winters. Now, what's interesting is, in our work, we were inspired a lot by Rod Brooks, and we were doing a lot of stuff like behavior-based robotics, which was very different from what we contrasted with traditional AI, things like, the tree search and perception and modeling, 3D world modeling and planning and stuff like that. It was fun. I enjoyed it. I was not doing things like neural networks, although what's interesting, somebody else in our lab was doing neural networks.
Yeah.
And I talked with him a few years ago and he said, it's great. It's coming back and my stuff is still relevant.
Yeah, I must say that I learned about neural networks in university in 2009, 2010. And then as students, we kind of acknowledged like, this is outdated technology. This is not state of the art. You shouldn't, use this too much. And then in 2014, of course, you got AlexNet. So we're like, oh, okay, interesting. Like good on the teacher for teaching us those neural networks. But let's see where it goes. And it kept blowing up and kept blowing up. Interesting experience.
So that's my weather report on the AI winter.
All right. Hey folks, have you ever wondered how software leaders pushing the boundaries in today's environment are adopting emerging trends? At QCon San Francisco, November 18 to 22, you will step inside the minds of the engineers who will share how they implement innovations in real-world scenarios. Explore tracks like architectures you've always wondered about, engineering productivity, and, my favorite, generative AI in production and advancements. Here you can learn from practicing senior software developers on how they are adopting emerging trends. Find out more about the conference at QConSF.com. We hope to see you there. All right. So what I wanted to do with you, Anthony, is take a look at an AI algorithm which was invented before the first AI winter and which is still relevant today. So you already talked about neural networks, right? Which was very much up, down, up, down. But I was thinking about what are examples of what people consider to be AI, but which kind of passed the test of time, where people can always use it. It's always relevant. It's always good. It's always interesting. And I think that, so the thing I want to talk about is A-star search. And I think most listeners are familiar with the A-star search algorithm. People probably heard of it at least. And I think that alone shows that it is an everlasting algorithm, that even if you're not into AI, you are still familiar with A-star.
I've heard of it.
Yeah. You probably had to implement it for some coding test. The one thing which I also find interesting about AI in general is that in the past, people would say, oh, search is AI, I don't know, world modeling is AI. Nowadays, you wouldn't really say that search algorithms are pure AI, would you? Or like if you talk about chess algorithms or something, you wouldn't really say, oh, it's AI, it's more like computer science.
Yeah, I tried to find the quote, and I know I'm not imagining it, but I couldn't find it. But there's a quote that's something like, AI just means something that computers aren't supposed to be good at. And once computers become good at it, it's no longer AI.
Yeah, I think I always summarize it as once it works, it becomes computer science.
Oh, that's awesome. Okay.
Yeah. This is one of these algorithms which became so good it became computer science. But so in terms of history, do you know when A-star is invented?
I don't. I'm guessing probably the 1950s or 60s, though.
Yeah, so it's invented in 1968 by Peter Hart, Niels Nielsen, Bertrand Raphael of the Stanford Research Institute. I will also put the paper in our show notes so you can read it yourself. And what's also interesting is that it was invented for Shaky the robot for his path planning. I will also put a PDF to that report in the show notes. I read both the original paper and looked through the report for Shaky the robot. And what disappointed me was that in the report for Shaky the Robot, they just mention using a breadth first search.
No A-star?
So that's what I find interesting, is that everybody always says, oh, A-star, Wikipedia says, oh, it's invented for Shaky the Robot. But if you look at the report, I think at some point they invented it, and then they already thought that even A-star was too slow to do a grid-based search.
Interesting.
So if you look through the paper, what I really like about papers which are this old is that they have very smart, inventive solutions for problems. So they are not doing a grid search like you would do nowadays. You would divide the room into tiles of like 10 by 10 centimeters and navigate between those tiles. They have something where they define the obstacles and then they have the tangent towards these obstacles so that the robot goes in the most optimal path around these obstacles and only plans from object edge to object edge. So the amount of search space becomes super low. So they don't even need to think of A-star anymore in the report.
With compute and other constraints at the time, they probably had to do a lot of these kinds of optimizations.
Yeah, and also what you mentioned before, in terms of representing images on punch cards, I would love to do more episodes around that. It's such an interesting topic. Maybe next season we have more time for that. The other thing to note about A-star is that it is similar to Dijkstra's algorithm, which we discussed as a fun fact at the start of last episode. But A-star, the big difference is that A-star is really point to point and not point to world like Dijkstra, where you calculate the distance to the entire world. And the thing I really like, for listeners who don't really know, A-star adds a heuristic. So you have a heuristic on how close are you to actually getting closer to the solution. So if you're going from point A to point B, if you're getting closer to point B, that's probably worth a point which you want to prioritize investigating first, rather than going back to the point where, like, imagine that you're navigating from Amsterdam to Paris. As a human, you just follow your finger towards Paris. You know where to go, and that's what you explore first. And then if you find that some road is blocked, then you backtrack and you start searching around it. And here what's cool is that the better your heuristic is, the more you can prune away from your solution space.
Right. Didn't this become really the core of a lot of chess playing engines as well?
Yeah, and that's what I really like. The versatility of the algorithm is super big. I've seen it being applied in Super Mario, where people had a heuristic on how to play Super Mario. They would expand the game state and then pick the state where Mario was the closest to the right boundary or something, or like had the most points, whatever. So I've seen it being used there. For chess, I think they use these trees, where you have some kind of probabilistic tree structure where you keep expanding, but you do keep estimating how many points you have or what your estimated win chance is. But yeah, they are super versatile. You have loads of different applications and not just mapping. And even when there is mapping, it's still, I think, one of the best algorithms. Whenever I have to program a search algorithm for anything, I try to think of how can I add a heuristic to this so I know that I'm closer to getting to the actual solution.
That makes sense. What's interesting is, we could probably do another episode on A-star versus something like reinforcement learning and the parallels there. Because that's basically what it is, right? How do you pick the next best action?
Well, so it's a combination between how good are you, or like what is your state, and where do you probably want to be, and can you keep expanding everything until you get closer to it. The one thing which I also, as I said, it's really an everlasting algorithm. So one thing which people probably noticed when they ever visualized or implemented A-star is that A-star can be slow if your heuristic isn't good, or if you just have a lot of space to explore. And you can see this if you go to the Wikipedia article. I think they have a visualization of like expanding a search horizon, not even a very big maze, but you do still keep expanding a lot of states. So I would say that if someone plans a route, I don't know, from one end of America to another end of America, you and I would just say, let's go on the highway.
Yeah, Interstate 40.
Interstate 40. So that's, I guess, your heuristic. But for mapping companies or for graphs, there is an alternative, right? Like contraction hierarchies is an example where you contract parts of the graph so you can ignore the smaller streets when you have to travel a large distance. So you just navigate the graph on a higher level and then navigate back down onto the smaller streets. So there are alternatives.
So you may not have studied this part, but how does it prevent getting into a cycle?
Oh, you keep track of what you already expanded.
I see. Okay.
Yeah, you keep track of which nodes you already visited. That's what I generally do. So because you know that A star found the fastest path towards a certain spot, you also don't have to expand it anymore afterwards. It's either expanded or visited. One of the two works.
Okay, nice.
Yeah. So just going back towards the everlasting aspects, as I said, there are for mapping nowadays, you would say that since 1968, there must have been better algorithms invented, right? So it's a long time. But what I like is that sometimes I talk to people working at map companies, and whenever they have to plan very specific routes, for example, imagine that you're a truck who can't go over certain bridges. Maybe you are a truck which has to ride on roads which are minimum this wide. Maybe you have customers who have a sports car and they want to drive over nice and windy roads with great views. There's loads of different customers who have demands for which roads they can take. And that means that once you have a lot of these different things to factor in, these companies just switch back to A star because this algorithm can always deal with any kind of constraints about what nodes you can and cannot expand to.
That's really cool. I never thought of that. It's that heuristic that you have to have lets you essentially guide your result so that it meets your constraints or your desires.
Yeah, the heuristic can be anything you want, right? So in the case of mapping, you would probably take a distance heuristic. That makes a lot of sense.
But you can also add like the windiness or the width or the something of the road.
Yeah, I guess that could be something where you say, for example, I think the trucks is a better example where if you have a pre-computed graph for a contracted graph for the highway, if that is one edge in your graph, you have to take the minimum part of your graph. Like if the maximum weight of one bridge is 2 tons, this entire edge becomes unusable for your truck. But with A star, you simply say, can I go over this edge with my truck? No. Okay, well then I don't expand this node. So you have one algorithm which can just handle everything.
I see. That's pretty awesome.
It is pretty awesome. The last thing which I want to encourage listeners to take a look at is a problem which Factorio had. Do you know the game Factorio?
Is that one of the ones with the snakes? Which one is this?
No,
that's Slither.
Slither.io. Yeah. No, Factorio is a factory building game, which is extremely addictive to people like me. If you enjoy automating things and solving problems, like most people who are programmers will, then Factorio is like crack. It is absolutely insane how addictive this game is.
Well, I'm going to stay away from it then.
Yeah, smart. Yeah. Sometimes I manage to convince a friend to download the game or buy the game. And then a week later, you see them with like black dots around their eyes being like, I haven't slept in a week. It's insane how this game just grips people. Anyways, the goal of the game is that you want to build a big factory and launch a rocket, but you have aliens on the planet, which you at some point can start shooting. So once you shoot an alien at a big distance from your factory on a landscape, the alien tries to plan a path to your base to start attacking whatever attacked him. And Factorio faced a problem that this pathfinding on these massive maps can be slow, especially if you have to plan around a big lake or something like that. So they already implemented A star, and the heuristic was simply the distance heuristic with what is the path around the lake. So A star was too slow, but you can modify the heuristic, right? And the heuristic is basically you want to get quickly back to the place where the fire originated from, where you want to go to. So what they did is they had a second search algorithm, which would search from the place they want to attack back to the aliens over all the tiles they deemed walkable. So they would divide the world up into bigger tiles. And then they would just calculate, can I cross this tile or not? Which is faster than having to do this for a massive map. So they have this very global idea. As I said, if you want to go from Amsterdam to Paris, you know roughly where Paris is, so you can really quickly expand in this direction. Or if you have to go around the lake, you have to go around the lake. It doesn't make sense to start searching away from the lake. So they modified the heuristic, which, again, most people are set to the Euclidean distance. But instead, they calculate a rough distance for each tile back to the place they want to go. And that way they can nudge the search very quickly in the right direction. And then they just still use the normal A-star algorithm with this new heuristic. So I will put the link to the blog in the show notes so you can read it yourself and see the visualizations. It's extremely cool to see how you can modify A-star and how much of flexibility you have with it.
It's like the Swiss Army knife of algorithms, huh?
Yeah, it is. It generally is a Swiss Army knife, which I love implementing. It's always fun. It's always good. It's easy and extremely efficient, and you can build in your own nudges and heuristics very fast. I love it.
I think they would have called it A++ or something.
Yeah, I think the reason for calling it A star was that the star was meant to indicate that this was optimal. I know there is something around where in the paper they mention that this is the optimal way to plan a path, that it always finds an optimal route. And then another researcher said, no, but you haven't thought of this constraint. So they published a paper about that, how that's not the case, that you should maybe modify something in the order you expand nodes. But then later, another researcher published a paper showing that, but it actually works. Like there was a mistake in the other paper. So it's a lot of drama around A-star.
I'm going to have to read up on it. I love drama.
Yeah, I mean, drama in the most academic sense, where someone finds a counterexample.
Well, it's the old saying that in academia, the fights are so brutal because the stakes are so low.
Yeah, that must be true. Any last questions about A-star?
No, as you can guess, I had heard of it and was familiar with it, but I wasn't aware of how useful it was, or how versatile and how long it had been around.
Yeah, it's a true winner of the land before AI winters. Always sticking around, always there, always trustworthy, always fast.
Just like the mammals after the dinosaurs went extinct, huh?
Yeah, I don't know how they came about, because breadth first search is also still around. It's just amazing that there's not such a versatile or easy to implement algorithm for this case.
Sometimes a simple thing is great.
It's exactly what you need. So, words of wisdom. Did you learn anything new this podcast, or did you learn anything yourself recently?
In one of those strange coincidences, I'd finished my last book. I picked up an old book, an old favorite, The Moon is a Harsh Mistress by Robert Heinlein, one of the great classics of sci-fi. And you may know that, spoiler alert, one of the main characters is a self-aware computer. And this book was written in 1966. What's interesting is in the very beginning of the book, part of the description of the computer is it has associative neural networks attached to it. So I thought that was kind of interesting and fun. What also is interesting, in this book, the computer learns how to do essentially a CGI version of a person. Like they made up a fictitious person, and the computer creates essentially a real-time artificial video, photorealistic video of the person, along with voice and so forth, which has never been done before in this universe.
Yeah. And it's still not done.
Well, yeah, we're getting there. What's funny, I don't know if you're an aficionado of classic sci-fi like Robert Heinlein. Robert Heinlein, his books in the 1940s and 1950s, he had a lot of space technology, like nuclear-powered, faster-than-light rockets, but all the navigation is done with slide rules and things like that. So he missed out on computers early, but by the 60s, he basically just jumped to, okay, computers are now self-aware.
Yeah, interesting. Yeah, I love the old sci-fi where if you read it now, you don't realize that these people didn't know what we have now.
There's a couple of old Heinlein stories from the 50s and 60s where characters essentially have cell phones, and it's just like a casual thing.
Yeah, if you read it now, you just think, oh, of course, I have a cell phone. But no, the guy had to invent cell phones in his head.
Exactly. Anyway, that's I don't know if that's words of wisdom, but it's something that I had not remembered.
It's a good fun fact. The one thing which I started looking at yesterday was the history of gliders and airplanes and parachutes. So the one thing which I discovered is, number one, the first aerostatic flight was carried out by the Montgolfier brothers at Versailles in 1783.
Yep.
That's interesting fun fact number one. That's quite a long time ago, right?
Yeah. And, I think, again, one of those stories that may not be true, but is really good. Supposedly, Benjamin Franklin witnessed this, and somebody remarked how useless it was. And he said, well, what's the use of a newborn baby?
That's one way to phrase it. Anyway, so then the other thing which I was wondering is then, when is the first parachute invented? And here Wikipedia says that the modern parachute was invented in 1783. It's the same year, right?
They jumped out of the balloon with it, I think, right?
Yeah, no, but someone jumped off a building, I guess. Also, I think at some point, someone invented a frameless parachute, and I think they brought it with them on a balloon trip in 1797. And then at some point they ditched the balloon, so they had to use a parachute, or at least that's what the person said. Like, oh, the balloon had problems, so I had to use my parachute. Maybe it was like sales talk, you don't know.
Probably we should caveat that it was the first successful parachute incident. Yeah. Somebody tried it before and did not succeed.
Yeah, the first time that someone tries a parachute is by jumping from a building, but then they invent these balloons so then they can jump from even higher. So in 1785, apparently someone demonstrated as a means of safely disembarking from a hot air balloon. Blanchard, I now read this on Wikipedia, his first parachute demonstrations were conducted with a dog as a passenger. Yeah, sad.
Just like the Russians, right? Sending a dog into space with the dog test out the parachute.
Anyways, the reason that I was looking at this was that I was reading the Mechanics magazine from Saturday, September 25, 1852, where George Cayley is talking about governable parachutes. So George Cayley has basically invented a glider here. So it's an airplane without any motor. So it's a glider. And he basically calls it a governable parachute. So I will also put this article in the show notes. It's quite interesting to read. Gliders, or like airplanes, were called governable parachutes before they were called gliders or airplanes.
They needed to workshop that one a little better.
I like it as if you don't have an airplane, what would you call it? And you do have parachutes because they have been around for a long time. Parachutes are old news now. So what if you can have a governable parachute? He also describes that to start this governable parachute, you can maybe hang it behind one of those air balloons. So his idea was to go up behind an air balloon and then release it and like have his governable parachute be steered.
He didn't have a fast enough motorboat.
He didn't even have a motor. This is before the motor. But
it had a steam train.
But as you say, motorboat, if you look at the illustration on the front page of this thing, he is sitting in what very much looks like a massive boat or a chariot. Looks more like a boat than a chariot.
Interesting.
Yeah, it's fun. Thank you so much for recording this podcast, Anthony. Thank you so much for the listeners for listening to this podcast. Please like it if your podcast platform has an option for this. And please tell your friends all about it and make sure that they listen to this.
Thank you, Roland. It's a pleasure as always.
Yeah, thank you very much for recording this with me, Anthony. I like it, as always. The only last fun fact I still want to tell you is that I think in one episode last season, I was complaining about my Apple Watch and that it didn't show the correct time. I'm done with it. it was still showing the wrong time last week. I bought a Garmin watch. I now have the correct time. And instead of the battery lasting for half a day, even though the watch is relatively new, I now have, 17 days of battery life.
Wow.
I like it.
And it works with your iPhone?
It works with my iPhone. Yeah, it shows my messages whenever they come in.
I might look into that.
Yeah, as I said, I was kind of fed up, especially if I would cycle to work, then cycle somewhere else, cycle back to my home, and then take a run. The watch would be dead. It can't keep up with an active lifestyle somehow.
Ridiculous.
Now, last weekend, I went on a hike. I walked 25 kilometers, had the map on the watch the whole time, and has only used a quarter of its charge or something. It's crazy.